Okay, class. Now we want to talk about a basis for a subspace. All right. As you know, the subspace normally contains infinitely many vectors. So in dealing with the subspace, we want to see if we can involve a finite set of vectors so that we can restrict our possible expressions of any vector based on a finite set of known vectors. So to do this, we want to see for any subspace, say H, is it possible we find a vectors v1, v2 to vn, that should be a 3 right here, that should be an n right here, n, okay, such that there's a finite set numbers of vectors such that every vectors in the subspace can be expressed a linear combinations of these vectors, v1 to vn. Can we find those vectors or not? So let's look at definition first. Okay, let's look at definition first. Definition of basis. Okay, the basis for a subspace H of Rn is a linearly independent set. Okay, linearly independent set that span H. Okay, that span H. So H is a subspace. We have three properties we talked about before, and then is when you're given a subspace, which is a set, it's possible to find a finite set of vectors such that every element in the subspace H can be expressed as a linear combination of these finite number of elements. Let's look at some example here. Okay, example. All right. So is here the three vectors 1, 1, 1, negative 1, negative 1, 1, a basis for R2. For R2. We don't know, right? But let's look at the picture first. Okay, 1, 1, 1, 1, that's 1, 1. And 1, negative 1, so 1, negative 1, 1, negative 1, the second one. And negative 1, 1, so negative 1, 1, that's the third vector. I have three vector here, okay? All right, by looking at the picture, I will say no, because you notice that 1, negative 1, and negative 1, 1, they're kind of what? On the same line, they're linearly dependent, right? All right, but the reason for not being assessed, the answer is no, since 1, 1, 1, negative 1, and negative 1, 1 are not linearly independent, right? So we can say, hey, 0 times 1, 1 plus 1 times 1, negative 1 plus 1 times negative 1, 1 equal to 0, 0. So I found a non-negative linear combination of the vectors such that I obtain 0 vector. So that's not linearly independent. So how can you make it linearly basis? Well, for any two vector other than these two, the last two, for example, these two together, they can express, well, combination of these two can express any vector on R2. Or these two together, they can express any vector can be expressed as a linear combination of these two vectors. The only two cannot be done is these two vectors, right? Because they are on the same lines. Anything not on this line is just too bad. You cannot express any vector outside of this line containing these two vectors. So I will say, however, they say 1, 1, 1, negative 1, or 1, 1, negative 1, 1 can be basis for R2. Any vector in here can be, if these two together, look at these two together, any vector here can be a linear combination of these two. You can express that. So as you can see, basis of a subspace is not unique